I'm Dinesh Kumar Sundarajan, currently pursuing my master's in the Department of ECE at University of Florida, and my project is face recognition by Eigenfaces method using MATLAB. So first of all, what is the need for face recognition? In recent times, there has been a significant increase in the number of electronic transactions. This has created a demand for fast and accurate user authentication systems. Say we can use PIN numbers for gaining access to buildings, secure areas, and the like. But what if these PIN numbers are stolen? Where is the proof for authenticity? This is where face recognition comes into picture. So what is face recognition? The basic concept is that every person's face has many features that are unique to that specific person. The face recognition techniques share a lot in common with the other biometric systems. So there arises a basic question. What is the difference between the normal face detection and face recognition? The face detection is a simpler technique which just classifies the image as a face or non-face. On the other hand, face recognition is slightly advanced, which sort of identifies which image matches to the test image from the database. There are two types of comparison techniques used. The first one is face verification. It's just a yes or no decision wherein two images are presented, and if the images match, it says yes, otherwise it's no. Face identification is a relatively complex approach wherein the image that matches the test image is displayed from the database. There are different types of face recognition techniques in practice. They are classified based on how the features are determined. If the features are determined based on local regions, there are two approaches in this regard. The first one is local feature analysis or Gabor wavelet. They basically take into account local features like eyes, nose, ears, etc. If the features are classified based on the global appearance, there are two major techniques adopted. The first one is principal component analysis, and second one is independent component analysis. The similarity measure between images is computed by using neural networks, Euclidean distance approach, template matching, and elastic graph matching. So the technique adopted for the purpose of this project is the Eigenfaces method. The basic idea is that instead of using the original images, eigenfaces are used for comparison. The eigenfaces are basically like ghostly images which are nothing but the eigenvectors of the covariance matrix of the set of faces. They represent the data more efficiently. Also in this technique, it is important to reduce dimensionality for speed and effectiveness, and this is where PCA or principal component analysis comes into picture. So what is principal component analysis? Let me just explain with the help of this small graph here. Say these two images x and y are two images are represented by these two axes x and y, and there's a third axis in between a. So which do you think is better to represent these two images? The one using the two-dimensional x and y, or the one using the single-dimensional a? The answer is the single-dimensional a. So this is basically dimensionality reduction, where a 2D axis, where an image present in 2D axis can be represented by using a single axis more efficiently. So PCA mainly helps in finding the principal components of the data. It builds n eigenvectors for an m cross n image that are ordered from the largest to the smallest. The largest eigenvalue associated with the vector, that is the one that finds the maximum variance present in the image. Say for in this particular image, if you consider x-axis or the y-axis, we won't be able to determine the maximum variance for the image. But rather, if we consider the a-axis, we will be able to obtain the maximum variance. So this is the salient feature of this approach, wherein around 90% of the total variance is present within 5 to 10% of the dimensions. And also the face space forms a cluster, but PCA gives a suitable representation. So this is the biggest advantage of PCA. So the face recognition system used as part of this project is represented in the following flowchart. First, the images in the database are read. Here 20 images are fed into the database, and the mean image is computed. Then the deviation of all these images from this mean image is found, and the centered images are computed, and the eigenfaces, or rather the eigenvectors of the covariance matrix, are found. The resultant image looks somewhat like this, and then we go into phase 2. The phase 2, shown in a different color, represents the recognition part of this process. This is where the test image is fed. Similar to the previous techniques, the eigenphase components are found for the test image, and Euclidean distances between these components and the ones already found are computed. Then the minimum Euclidean distance among all of them is found, and if this value is greater than a particular threshold, we declare that the image does not match any of the data present in the database. If the minimum Euclidean distance is lesser than a particular threshold, we display the matching image from the database which has the minimum Euclidean distance. So we'll go step by step right now. The first step is obtaining data from the database. So as you can see, I've presented 20 images in the database. So this is the data considered for the face recognition process. The second step is finding the mean image. The mean image is computed based on this formula, and I've also shown the code snippet that I've used for this process. So, and you can see the image, almost like a ghost here. This is the mean image of these 20 images. So this is the mean image. So after the mean image is found, it is important to find the deviation and centered images. The deviation is found by subtracting the value from the mean image for each individual images. The centered 2D image matrix is then found. This is the code snippet used to find the centered image based on the deviation. This step, or step 4, the eigenfaces computation, forms the crux of the project. The covariance matrix is found using the centered image, and this is the formula used, and C represents AA transpose, and the eigenvalues for this covariance matrix are found, and the set of non-zero eigenvectors are computed. The eigenvectors which fall below a particular value of threshold are eliminated. This is basically the dimensionality reduction technique adopted in PCA. And so continuation of eigenphase computation. The resultant eigenvectors represent a set of ghostly faces. So as you can see, these 20 ghostly images or eigenfaces represent effectively the original data. We can use these images for comparison instead of using the original image. This saves considerable amount of time, and it's a lot more accurate. So going into phase 2, now we are feeding a test image into the system. Say for example, this is the text image that is fed, and the steps which I explained, the previous steps, are repeated for this test image again, and this is the corresponding code used to read this image. And the Euclidean distance between this test image and the previously computed eigenfaces are found, and as you can see, they are plotted here, and it shows that the lowest value is for image number 14. This is the code snippet used to compute the Euclidean distance value, and this is the lowest one among all. So as you can see, the image that is tested has the lowest Euclidean distance is obtained in image number 14, and the matched image from the database is shown here. As you can see, this subject or this image has spectacles, and the face recognition system is so effective that it can still match the image from the database. And also, even though it's the image of the same person, we can see that the person is showing different expressions, but this system is still able to recognize that. So now going into a small demo. Before going to the demo, I just want to show the list of images used for training and testing. So these are the set of images used for training. It's a random set of images. It has pictures of myself, some of my friends, and some random copyright-free images that I found on the internet. And these are the data used for testing. So it has 11 images. One important point to be noted here is that the first 10 images has corresponding matching images present in the training database, and this 11th image right here does not match with any of the images in the database. So going to the MATLAB code right now. So first we get to choose the training database. I just choose that, and as stated, the eigenfaces and the mean images are found. The next step is choosing the testing database, and now I'm just going to give a random image for testing purposes. It's a random number from 1 to 10. I'm just going with 4. Okay, so as you can see, so this is the image to be tested, and this is the corresponding Euclidean distance graph. As you can see, the lowest value is obtained for image number 9, and the command window of the MATLAB displays the image in the training database that matches the test image is 9, and this is the 9th image from the database. Again, as you can see, these are images of the same person who's showing different expressions, which is captured beautifully by this technique. Let's just go for one more trial, and these are the eigenfaces computed, the mean image, and this is the train database. Let's select one more data. So this time I'm going for the spectacle subject. So again, I'm just choosing some random number. Oh, okay, so it's the same one as shown in the presentation. So as you can see, again, the minimum Euclidean distance is for image number 14, and as expected, the MATLAB displays the matching image is number 14, and this is the matched image from the database. It can be noted that even though the subject is wearing spectacles, this algorithm works efficiently. Now let's also test the image which is not present in the database. It already said earlier that image number 11 from the testing folder is not present in the training database. So I'm going ahead and I'm choosing number 11. It's not present, so here it is. So as you can see, it says the test image does not match with the training data, and this is the corresponding Euclidean distance of the test image. If you notice, this graph is much more taller and the values are much larger than the previous ones, and I've set the threshold value as 0.5, and as you can see, all these values are above this threshold value, and hence it says the test image does not match with the training data. So going back to the presentation, finally I would like to conclude by saying that an efficient face recognition system using the Eigenfaces method was implemented successfully in MATLAB. 3 different test images were provided, and the face recognition system was found to work very efficiently every single time. Even though the Eigenfaces method has been around for a really long time, the novelty of this project lies in the simplicity with which face recognition has been carried out. As we all know, there are many applications for face recognition, like surveillance. They are used in law enforcement agencies, for human-computer interaction in different universities. If you notice, the main step involved in the Eigenfaces method is computing the eigenvectors. So the future scope of this project would be in choosing these low-dimensional eigenvectors more efficiently. This would lend more accuracy and credibility to this system. So these are the various references that I have cited during the course of this project, and thank you all for patiently